All right, and so the plan is, I think for today through Thursday, is get some of these concepts down in chapter 17. Not get them all down because we don't have enough time, but we'll get a lot of them down before Friday, and then Friday I'll let you guys review and study and look off your old tests and give you a review sheet, and you can do that all for the semester final. So you can, and I'll give answers to the questions for chapters 1 through 6, and then chapter 17. So there'll just be it's a cumulative review, and you guys can do that on Friday. You can ask questions on Monday. I think what I'll do is I'm just going to include chapter 17 in the semester final and not give you a separate test. So then you guys can focus on doing some of chapter 17 and knowing how to do that for the semester final. And so there'll be a few questions on there from chapter 17. And then it'll be filled with other questions on chapters 1 through 6. I try not to make it too difficult, in that I try to do lower level and middle level and not very many upper level type of questions. Does that make sense? So you'll have, and there'll be a lot of them will be multiple choice. Be a lot of them, even the problem-based ones, where you got problems to solve. You'll have 4 selections, and you'll have to pick out the correct selection that you have for that. All right, any thoughts on that? So we did some things with entropy, and on page 670, let's just kind of review. Positive entropy means that it goes to more disorder. All right. If you look on page 871, there's the second law of thermodynamics. The first law was what?
Energy is constant.
Yeah, energy in the universe is constant. Doesn't change. So if something gains, something's got to lose. And it's the same amount. So it's always going to be constant, and that's how you can use that law in which to show endothermic and exothermic loss and gain of energy. On page 671, it says, in any spontaneous process, there's always an increase in the entropy of the universe. So what does that mean, entropy of the universe? What it means is when you take the system and the surroundings, and that when something's spontaneous, and we'll talk about what spontaneous is later, we might not get to it today, is that you're always going to have an increase in the change of S for the entropy. So just, I want you to think about that, keep in the back of your mind, and once we get into looking at spontaneous reactions, that'll make more sense. All right, so on page 670, what do you guys think is the change of entropy? Now they do give the answers down below, so don't look down below. So when a solid CO2 goes from a solid to a gas, what do you think, is that a positive or negative change in entropy?
Positive.
Positive. This goes to more disorder, so it's a positive. And so when we take a look at spontaneous reactions, a lot of them will go to the point where it's wanting to go to more of a random, less organized to less organized composition of matter is what it's going to go to and from. So if we have solid CO2 going to CO2 gas, then that change of entropy, change of S is entropy, and it's positive. So anytime you see S, that means entropy. So that's positive. So what if we have N2 gas that's at 1 atmosphere, and then we're going to N2 gas that has a pressure on it that would be 0.01 atmospheres. Or 1, they say 1 times 10 minus second. What do you think that's going to be? What's that? Increase. Now, why would it be an increase? Yeah, so less pressure and they're spread out more. So, and we know it has a bigger volume. So it's going from maybe a volume like this to, if it's 0.01, it's going to be 100 times bigger volume. And that's probably not the correct relationship on that. But it's going from a smaller volume where they're closer together to a larger volume where they're further apart. So you might have them close together here, nitrogen, and then over here, if you have 3 of them, they're much more spread out. Okay, so they're more random. If you would read through at the start, and it's up to you if you want to do it or not, they give you some examples of that, more of a higher entropy and what that means. So that should be a change of entropy that should be positive, right? Questions? How about at the bottom there it says solid sugar added to water to form a solution. So we're taking sugar, C12H22O11, okay, and we're taking it from a solid to aqueous. What do you think? Positive or negative? Positive, right? So the change of S is positive there because it's going from a solid, now it's going into H2O, where it's splitting down into individual C12H22O11 molecules that are kind of in between all the water molecules. So more disorder to that situation. Okay? And then the last one, iodine vapor condenses on the cold surface from crystals. So we got iodine vapor going to iodine solid. Or not solid, liquid. Oh, to form crystals, so it wouldn't be a solid. So what would it be? Change of entropy would be negative. How many questions you guys have on that? Okay. What I'm going to have you do is I'm going to have you turn over to page 680. And I'm going to have you guys predict these signs for change of S, just like we did. But these are chemical reactions a little bit more. Don't look at the solution down below. Just look at A and B, and then write down what you think. And if you want to look at what the answer is supposed to be, you can look down below before we go through it. So the first one, is it positive change in entropy or negative? So it's going from 1 mole to 2 moles. And it's also going from 1 mole of a solid to a mole of a solid and a mole of a gas. So what would it be? Change of entropy would be positive, right? Anytime you got a reaction that goes from 1 or less moles to more moles, then there's more disorder. Okay? So this one's going from 2 gases, where we have 3 moles, to 2 moles and 1 gas. So what do you think the change of entropy there would be? Negative. Okay. So you kind of get an idea. Now you're predicting these. A lot of these are being predictions, but most of the time they're pretty good. Yep.
What if it went from like 2 moles of a solid to 1 mole of a gas?
So to 1 mole of a gas.
Yeah.
I don't think it.
Can I not do that?
Yeah, I can. Let me give. To 2 moles of a gas.
To 2 solids and 1 gas.
Okay. I can give you a situation where it goes from a gas to a gas. So that deals with moles, but I. So it would be more organized. Both things would show it be more organized. You're going 2 to 1, so it's more organized. You got some things coming together where they were separated, and then now you're also going to a solid, which is more organized than a gas.
Right, but you're going from solid to gas.
A gas. In that situation, it's kind of they're going against each other, so it's kind of tough to predict. These are just predictions. You got to realize these are just most of these predictions are right. If you would look at them. Okay, so yeah, good question. On that, you'd have to have some more information.
Okay. That makes sense.
Okay, so turn over to 682, and we're going to do a real quick calculation of change in S. So in the back of the book, you have where you had change of enthalpy, you have change in entropy. So go ahead and look at the back of the book, and your appendix A22, or starting at A21.
Is it the S?
It's the S. Yep. So you have Al2O3 solid. And you guys, by the way, did really, really well on these on the test. And these are exactly the same as change of enthalpy, but they just have a different number associated with them. They're joules instead of kilojoules, for one. So when you calculate these are joules and not kilojoules, because enthalpy was kilojoules, and these are joules per mole, is what the value is. So before we do this, let's see if you guys can predict, what do you think the change of entropy is going to be before we even do the calculation? So looking up here, what do you think? It's going from a solid gas to a solid and gas. It's going from 4 moles to 5 moles.
It's going to be negative.
So do you think it would be negative
Positive.
or positive?
There's more moles.
So more of them usually means more disorder. So your prediction, according to what we've been doing, should be positive. So we should end up with a positive entropy change. Okay. So you don't have to look on this page. They're given to you there. Aluminum oxide is 51 joules per mole. Hydrogen is 131 joules per mole. Now, on these, they're not 0. Like enthalpy, hydrogen would have been 0. And aluminum would have been 0. But that's not the case on these. Okay, because they all have some sort of order related to the other ones. And then water is 189 joules per mole. So just like before, this would be 51 joules per mole, because we only had one of them. This would be 393 joules per, wouldn't be per mole anymore, because the mole cancels out when we multiply moles by the number. So 51 joules, 393 joules would be the right side, so that would be what, 444? Okay, joules on the reactant side. And over here we'd have 56 joules. And then 189 times 3 is Somebody calculate that for me.
567.
567?
Mm-hmm.
Okay? So 567, and then add those together. That would be, what, 1,000?
Oh, it'd be 6.
Oh, I'm sorry.
23.
I'm thinking 560. So it would be 623. So then you take the 623 joules minus 444 joules, and it is positive, isn't it? And then you get your change of entropy. So it'd be 179, right?
The
So-
book is leaving them as joules per Kelvin.
Right. Because it's based upon the Kelvin temperature, right? So, yeah. Joules per Kelvin. All right. Questions on that? Okay. Then we're going to do this same one, and I'll explain later what the delta G is. Okay, so delta G is something that's going to tell you if something's spontaneous or not. So delta G is taking two things into consideration: enthalpy and entropy. So it's looking at, is it exothermic or endothermic reaction, and what's the change of entropy? Is it positive or negative? So the delta G, that third one there, tells you a lot about if it's spontaneous or not spontaneous. It says, you know, if it's negative, it's going to be spontaneous. If it's positive, then we come up with a calculation. But I don't want to go too fast in that. So I'm just going to show you how to do the calculation. We'll do the same one here, and do one real quick with a delta G. You guys will know how to do it because it's the same as delta H, or the enthalpy. So I'm going to go to, let me do something here real quick. And so we'll do delta G. And then I'll explain what the delta G tells you here. But I don't want to go too quick on this whole process. So you have how we found change of S. Now we're going to do change of G. So we're going to look these up. You guys help me look these up. And you since you're back there on A22, what is aluminum oxide's delta G?
Negative 1,582.
1,000, what is it?
582.
582 kilojoules per mole. Hydrogen? Or aluminum or water?
Hydrogen 0.
Okay?
Aluminum,
Is it 0?
yeah.
And water?
I think it's a gas. Negative 229.
Okay, so we'll just add that up. So that would be 687 for that one. Okay, and that's in kilojoules. And then this is a negative 1582 kilojoules. So then we take 687 minus 1582 kilojoules, and that gives us delta G. So then delta G, we're just using those numbers. And it is going to be positive.
Is the 687 negative?
Yeah, I'm sorry. So it would be a negative 687 minus a minus 1582. So it's 895. And that's what it would be for the delta G.
Oh, delta G tells you something's gonna be spontaneous.
Yes, it tells you if something is a result of it's going to be positive or not. So if it's positive, it's not favorable for a spontaneous reaction.
Okay.
So this is not, this would be showing that it's not favorable for, if it's positive, it says it's probably a non-spontaneous reaction. When you put Al2 and O3 with H2 and just let them sit, they're probably not going to ever react. But if we have another situation where we do it and we come up with a negative and we put them together, it's probably going to react. It's probably going to naturally react spontaneously. So we'll get into that later this week. We don't want to get too much too quick in that. So I'm going to give you an assignment, and then we'll just have we'll take a look at it on Wednesday. Okay? And so if you turn to the back of that section, then I'll have you work on some of the things we've been working on. And that would be page 702, starting on A, the 45. Now, a lot of these you can look up the answers. So, some of you like doing that just to see if you're doing them right, which is fine. So 45, actually it'd be 47 through 50. And 58. You can do that for Wednesday. And then we'll talk a little bit more tomorrow about spontaneous and non-spontaneous and making predictions without doing actual calculations. So, okay. We'll do that tomorrow.